All right, let's test this. Power on the X16. Oh man, would you look at that? It works, it freaking works! Well, hello everyone, and welcome back to Adrian's Digital Basement. Today's video is going to be a little bit different. I'm going to be talking about the Commander X16. This is a new computer that's being developed by a group of enthusiasts out there. I think most of my viewers are probably aware of this machine because 8-Bit Guy has had several videos on this machine already, which have been in development for a good amount of time. The reason why I'm talking about this machine is this right here is a prototype that was sent to me from Kevin at Texelec, who is the guy who designed this hardware right here, and they needed some help in troubleshooting it. Now, I think a lot of my viewers, or some of them at least, are not only familiar with this, but are familiar with the fact that I had actually been working on this, because Kevin at Texelec has put up a video on his channel talking about the status of this prototype and the fact that it's working, and he thanked me by name for helping him getting it working. And I had several viewers come over to my channel and say, hey, what's going on with this? Can you talk about it on a video? So I guess I decided to do that, to talk about this. I wasn't originally gonna make a video about the Commander X16, and that was because I wasn't actually sure how much I would really be able to help with getting this machine working, this prototype that is. So I didn't really film anything or prepare or do any work. I just sort of worked on it, had lots of conversations with Kevin at Texelec. He has the other prototype at his house. So I don't think there are many of these that exist. This is the Generation 2 prototype. And he built this specifically and had it sent out to me last month. I think there might be one other one floating around that doesn't necessarily work. But you notice there are some bodge wires on here, and these are things that I came up with to try to get this thing working. So I thought in this video, perhaps I'll talk a little bit about this, what it is actually. We'll kind of start from there, give you some info on links to check out if you want to know more about this. And then I will talk about the things that I found that were weird with this particular prototype that prevented it from working. And I'll talk about these bodges, and maybe that will give people some information. Sorry, I'm a little all over the place with this. I'm not gonna script this. I'm gonna do minimal editing, and I'm just gonna talk about this off the cuff. So this is gonna be a nibble size video, not long, and we'll return to normal mail call videos next week. So first, let me show a close-up of what this is, and I'll talk about a little bit more about the Commander X16. I mounted my camera on my little tripod mount above my workbench here. I don't know why I don't do this more often. Actually, it's a bit of a pain to get the camera mounted on there. I have to kind of twist it around and around onto the tripod mount. I really need to figure out some kind of a quick release mechanism so I can move the camera from the tripod, which I have a pretty crappy tripod, onto the camera mount that's up on the bench here. That way I'm not constantly having to fiddle around, and I can do it very quickly. And I will use this overhead mount a lot more often. I think it's a much better camera angle, especially if I'm doing work on something, than that over-the-shoulder one I typically use. Anyways, okay, so the Commander X16. What is the Commander X16? So as I mentioned, this is a project that's being worked on by several retro computer enthusiasts. I am not totally clear on exactly the history. I don't know if David Murray, 8-Bit Guy, came up with the whole idea from the very start. He is definitely a big proponent of this, and there are a lot of people involved doing various aspects of this design. I have not worked on this at all up until this point. I've only been like everyone else, and I've seen the videos on this, like on 8-Bit Guy's channel. And I was pretty excited. I thought it was a cool project, but I didn't really know a whole lot about it. So really, to summarize what the Commander X16 is, this is an 8-bit computer. It's running a 6502 processor. It's a brand new design, so it's designed from scratch. Like, this is not a VIC-20 on steroids or a PET on steroids. This is really a new design entirely. And the whole idea was to make the 8-bit computer from the old days that everyone wanted. So it's got a 6502, so it's good and easy to program, but unlike say, Commodore machines of the time, it has expansion slots, and you can see them 4 slots right here. Also, it has a lot of RAM and a lot of ROM. So this is the ROM chip right here, and it's 512K of ROM. So the address space on the 6502, of course, is only 64K. So the memory map of this thing, which I'll put up on the screen right here, it's using banking. So the ROMs are banked, so you have like regular ROM space, and you can bank out that entire ROM space with a whole bunch of other ROMs that come from the same chip for up to 512K of ROM. Then this is all RAM. There are 5 RAM chips here, each one being 512K. Now the first one, unfortunately, you can only use 64K of this, or not even 64K. Actually, I think you can use 64K, but only a fraction of this chip is actually used. But the other 4 chips here are 512 each, and all of these can be used and banked into a high memory address space in the machine. So really you have the regular address space with 0 page and everything, and then you have an extra 2048K available. Now this is a preliminary design. This is the 2nd revision prototype, and there will be hardware changes that come up in the future. So this may not be the final design. In fact, some of the things I hear that might be happening is there'll be less memory on board, like maybe only 512K as opposed to 2 full megs, and some other minor changes, which I'll get to in a second. So continuing on what this particular prototype has, there are 2 6522 VIA chips. These were used in the Commodore 64 and on the PET as well. One of them is primarily used for the IEC port. So there's a standard IEC port right here for hooking up Commodore disk drives and stuff like that. There will be right here that's just not on this board, but there's a PS2 keyboard and mouse, because that is how this will work. It will interface keyboard and mouse. There is a clock chip right here, and the clock chip is like battery backed up. There's a battery holder right here. So the clock chip has a little bit of NVRAM, so it's like a BIOS. You could store configuration options, things like that. There's a little clock crystal there. I think this is one thing that's going to be changing. The way this interfaces to the board, it's sort of silly and complicated. So this might be changing to like an SPI type clock NVRAM, which would be interfaced through these VIAs. In addition, and I'll flip this over, there are 2 headers here. These will be Super NES controller ports. So this will use standard Super Nintendo type controllers, and those are through the VIAs as well. So I think it's this top one that's doing IEC, keyboard, mouse, and Super Nintendo ports. So that's for joystick. So it's not going to be using the standard 9-pin joysticks that like Commodores use. So you'll be able to have a full range of buttons, which is pretty sweet. This 6522 here is controlling, I think, this user port. I've looked at the schematics a whole bunch, but I've kind of forgotten how exactly everything works. But this user port right here, which is like compatible with a parallel port on a PC, but also could be wired up as a normal user port, like on a Commodore device or whatever. It's just general purpose input-output, and that's from this one here. The expansion slots here are completely wired up to be able to, say, replace the CPU with another CPU, like a 65C816 if you want that. You can also, there's extra I/O select lines that go to these. So you can, these are extra I/O ports, and allows you to, really add functionality to this machine. Anyhow, with the current design as well, the way you access the banked RAM and ROM is through select registers. And it's similar to how the 64 works actually, where in the 0 page, address 0000, the very first address in the address space, and 0001 are used to control I/O lines on the 6510 processor that's on the 64. That allows you to bank RAM and ROM in and out, so you can overlay like a ROM on top of the RAM and do various things like that. And on this, this logic up in here, these ICs, this is for selecting which bank you're going to be accessing here. So you basically write to those registers at 0000 and 0001, and that lets you select on the fly which ROM and RAM banks you're using. And then the very last thing, well, actually, there's 2 more things to talk about. There is sound capabilities on here. So there are 2 sound chips on this prototype, which I think is going to change to 1 on the prototype or on the future boards. So this chip right here is a YMF. It's a Yamaha. I think I wrote on here what it is. 21, is it 2151 or 2141? It's an FM synthesis sound chip that's used on a lot of arcade machines, a lot. In fact, like Outrun, Sega game Outrun used this exact chip. Tons and tons of games used it. Outrun did have a digital sound channel as well that was not through this chip. So, you know, when you hear that music, the percussion and stuff, I think is coming through digital. But anyhow, it's a pretty cool sound chip. It's still available, you know, obviously from China because there's their surplus chips at this point. I don't think they're made any longer, but it's a pretty cool chip and has some really cool sounds to it. Really neat FM sound. And, you know, if you're familiar with the Ad-Lib chip on PCs, that YMF, similar sounding, but slightly different. So that's pretty cool. There's an SAA 1099 sound chip right here. It's this small IC. That IC is like square waves. I think it's 6 channels. It's used in the Creative Labs CMS, Creative Music Sound System. It's the precursor to the Sound Blaster. And it sounds pretty cool, actually. It's square wave, so it sounds like a Nintendo Entertainment System, but it has 6 channels, and it's also stereo. So you can have the channels pan left and right and stuff like that. Unfortunately, I think this sound chip is going to be taken off the next revision. It's not going to stay. So, but don't worry about it because this thing has other sound capabilities that surpass what this can do anyways. And it's just, you know, while those square waves sound kind of cool, there is the YMF chip here that will be staying, but there is more sound to come from something else. So the final component right here is this board here. Now this is attached, as you see on these standoffs, and this is the video card. I think it's called the VERA. Well, it is called the VERA, V-E-R-A. And this is actually an FPGA. And the FPGA is connected through this pin header down here. And it is selected through like a regular I/O select line. It's on the data bus and has a couple address lines. And you basically write to registers in this. And this has the video memory in here. It's VGA output. It has composite output and has S-video. And it also has an SD card slot, and this actually has sound capability as well. So when you use the VERA for sound, it's actually sent back into the board and it's mixed with the sound chips over here, which is the YMF and the SAA 1099. Well, that's going away. So the sound that comes out of this can be mixed with the YMF. So you can still use both at the same time, and that is quite cool. There is, like I said, an SD card slot on here, which is incredibly fast. The way the VERA works for reading and writing the memory on this card is pretty efficient in that it auto increments. So you're using these registers to read and write to it, but every time you hit the register to read, it auto increments the address pointer. So you just keep reading from that same address over and over again in the IO space of this card. And it allows for super fast data reads and writes. It's basically almost as fast as the 6502 can copy data from one location into main memory. I mean, it's super fast. So that's the way the SD card reads work as well. It's amazingly quick. So there's nothing to worry about from a throughput standpoint. The capabilities of this are all outlined on the Wikipedia article, or not Wikipedia, on the wiki for this on Commander X16. I'll put links in the description. It's like 640 by 480. That's the native resolution of it. But of course you can alter the way the screen output is to be like 320 by 240. And I think it has enough video RAM for like 256 colors and has color palettes. So you can do color cycling, and it has tile maps. So, you know, you can have tiled graphics and larger play fields. So you can like scroll around just like the way like a Nintendo works or something. So it's really well suited for things like games that do lots of scrolling, horizontal, vertical scrolling. It has full sprites, collision, you know, all sorts of stuff like that. It's pretty amazing actually what this thing can do. I'd say, you know, having played around with it, I wrote a little bit of assembly to test this thing. The only thing I have to say that maybe I'm not in love with this is that the RGB output, the VGA, you can either run at 31 kilohertz, so like native 640 by 480, or at 15 kilohertz, which is like NTSC rates, as the same. That's obviously what the composite in the S-video run at is 15 kilohertz. But the output at 15 kilohertz is always interlaced. There is no way to get a non-interlaced signal out of this thing. You cannot get 240p, at least that I'm aware of. That's the documentation. It's just not possible right now. Being an FPGA, of course, it's possible that maybe with an upgrade it could do that, but right now it can't. So even though you can output like to a composite monitor right now, there is no way to get a really crisp 240p image like you would on a real Commodore 64 or VIC-20, things like that. So obviously I think most people just use a VGA monitor and it's fine because it's going to be, you know, 480p through VGA anyways. But I personally would have loved to have had a retro option to give me 240p on an old school monitor. But anyway, this thing is pretty amazing. So I mean, one of the things about this whole design was it needed to use all components that were still available, not something like a VIC-2 chip that's hard to find. So everything had to be currently manufactured. I think the YMF sound chip's the only one that's not currently made, and that's because there just really are no good sound chips left anymore that are like FM chips that would interface to an 8-bit computer like this. It's just a side effect of the fact that everything sound-wise now is done, you know, through CPU mix, software mixing and stuff, and you just have a simple DAC. That's how everything works these days. So that's the one I think compromised, but everything else on here is through hole, nothing is surface mount. Let's ignore the VERA for a sec, right? But all of the main board, everything is through hole, easily assembled. The idea will be there will be a kit available or fully assembled boards. And the VERA is the only thing obviously that's like crazy, is all surface mount. So from my understanding, the decision was made to go with an FPGA-based video solution. And I know people are gonna be like, oh, there could have been something else. But I wasn't, like I said, I wasn't part of the design team to come up with the design of this at all. But having chatted with Kevin a lot on this particular project, I am fully aware, and I think David Murray, 8-Bit Guy, has talked about the fact that there just is nothing good. There are no good video chip solutions available right now that would offer good modern graphics at VGA resolutions with like all the high color scrolling, all the fancy features that everyone really wants. So that's why this was chosen. Now the FPGA on here, from my understanding, I'm not sure which one it is, but it's not a super powerful one. So, I mean, yeah, I think it's powerful enough that it could like probably emulate the entire computer, like, or at least the 6502. But it's not that expensive. You know, this is not some super high cost FPGA that's gonna mean that this VERA board is gonna cost a lot. One of the other things that I think will be possible, and I've sort of talked to Kevin about this, but I mean, you know, like I said, I'm not part of the design team, is there's no reason why this VERA, this video card, wouldn't work perfectly on any other 8-bit machine. Apple II, VIC-20, PET, Commodore 64, anything. Any Z80, Z80 based computers too, all of those could interface to this perfectly without any issue. It's super, super simple the way the bus works, the way this thing interfaces. So theoretically, this could be, you know, put on a little adapter card in an Apple II and give your Apple II 640 by 480 by 256 colors with scrolling and all sorts of crazy capabilities. I mean, sure, it can't replace like the built-in graphics on Apple II, but software could be very easily ported and written to, you know, use this card on all sorts of things. And I don't know what this is going to cost, like what the VERA costs as a board. It might only be maybe it's like $25, $30, $40, even $50. $50 for one of these on like a simple PCB, a passive PCB in an Apple II, seems like a pretty reasonable price for like a pretty amazing piece of tech here from a video card perspective, right? I'm pretty impressed. Oh, and one of the other things about this particular board is that it is designed to work at 8 megahertz, and it has a jumper here to select between 2, 4, and 8 megahertz. So, you know, there is a selectable speed, but ultimately the real design is 8 megahertz. I mean, why would you run it at anything less than that, right? So that's pretty cool. So it's significantly more horsepower than any of the older machines because a 6502 is a pretty efficient processor. It's just not wasting a lot of time, which is why a 1 megahertz Apple II is pretty comparable to like a 4.77 megahertz 8088, for instance. An 8088 is not a very efficient processor because it's like a 16-bit CPU on an 8-bit bus, so it has to like do double writes, and it has the address bus and the data bus is multiplexed. So there's a lot going on with an 8088 that makes it inefficient and slow, at least in that form factor. Once you get to 386s, there's enough pins for everything, so it's a lot faster. But a 6502 running 8 megahertz is really fast. And on a machine like this, there aren't any wait states. This is running at full speed, talking to the RAM at 8 megahertz. So it's easily 8 times faster than any of the computers of the time of the, you know, Apple II, Commodore era, right? 8 times more power on this board, but still running the same assembly code. So anyone who's good at assembly language or programming, those old machines can program this thing just as easily. Everything is well documented on this. All the chips it uses are nothing custom, except for the VERA, but has very clear documentation. Everything else is really easy to interface to. So you want to like write to the user port here? Well, it's just a 6522. It's used in many computers. There's tons of code out there to use it. So anyhow, it's all really exciting. You know, I don't know how far away this is to release, but here's what happened. There was a first version of this. I think the board was like a red color. First revision, it didn't have the slots. It looked a bit different. And the video subsystem was different, not to mention the way the banking all worked. So Kevin at Texelec, he came up with the second version, had them made, put it together, and unfortunately, when he did, it didn't seem to work. It just, he had everything running on the first prototype, the first revision, but this version 2, it just didn't work properly. They were kind of stuck, so to speak. A bunch of time had gone by and there just wasn't a lot of movement. He kind of couldn't really figure out what to do. He had been talking to people like Bill Hurd and other people who are very knowledgeable about it, and they gave, of course, tips and stuff, but it just wasn't moving anywhere. So with the December stuff that was going on in December, I was in contact with other YouTubers, including David Murray, and he hit me up and he was like, hey, can I talk to you about something? And I'm like, yeah, of course. And so we chatted and he's like, hey, we have this project, if you're aware with it. And of course I was, because I watch his videos. And he's like, we're stuck. And I was wondering, he's asking me, he was wondering if I could help maybe take a look at this and see if I could figure out what was going on, why it wasn't working anymore, so we could start making some progress. I've said, of course. And I'm like, oh, sure, of course. I mean, I don't really know what I'm doing. I mean, I'm just a hobbyist, right? But I've done enough troubleshooting now that I thought this is just another 8-bit computer. And like I complain about when there's no schematics, it's really hard to fix stuff. But there are schematics for this. They're not publicly available yet. But Kevin at Texelec, he built up one of these prototypes and he sent it out. This is the one right here. He sent this out to me. And he sent me a copy of the schematics as well so I could take a look at how it was designed and try to figure out why this thing wasn't working to see if I could help get it working. So this is where I started troubleshooting this board to see if I could figure out what was going on. Now, if I remove these little clipped wires here, the way I got this board, it pretty much looked like this, except minus these little red bodge wires. There were a couple bodges on the board already, like this right here. This was a 74 LS 245 that he had removed. It's for the sound circuitry, so he just bypassed it right there. There's a little pin right there that's been bodged, and that was like he had figured out already that needed to be done, so he did that on the board he built me. And the only other thing you may notice is that this sound chip, or this chip right here, is missing. Now I took that out, and I'll talk about why in a second. Now, unfortunately, there really isn't hardly any code for this, and that's because between the first revision and the second revision, things got changed. So pretty much nothing was running on this. Like, you couldn't run the stock kernel, which is like the emulator, which boots up to a Commander X16 screen. That wasn't compiled or working for this board yet. And he had just been trying to run some test code to, say, generate some sound or drive a little LCD screen, stuff like that. But seemingly nothing was working. And personally, I don't really know that much about 6502 assembly. I know a little bit. I'm not completely useless, but at the same time, I'm not an expert. I've never actually written any 6502 assembly. So needless to say, the way it works is you have to take the ROM chip and put it in like a mini pro, like my EEPROM programmer, and flash some ROM onto here. So when the computer boots up, the 6502 starts executing code out of the ROM. And since there's no kernel, we would just put a jump statement that jumps to the ROM code to start running the diagnostic tests. The code he sent me was supposed to generate some sound out of the YMF chip, just some notes and stuff to sort of validate that things were working. And when Kevin had initially tested this at his house, like on his prototype, he could see with his logic analyzer stuff running. So it was like doing stuff, but he could never get anything working. He could never get the sound chip working. He hooked up an LCD screen. That never seemed to work. This is the little ones you would use your Arduino. Nothing. Couldn't get anything working. I think he had some VERA test code that should say hello world. That would never run. Like, it would never initialize the video. It just seemed like nothing was working. So with the board in hand, I connected it to an ATX power supply. As you see here, it has an ATX supply header. In fact, that's one thing I didn't mention. This actually conforms to the ATX form factor so that you can put this into any ATX computer case. And the one you see, the prototype case that's on the website, is an ATX case, but you don't have to use that. You could just buy this in the future once it comes out and stick it in any ATX case. And it uses a regular ATX power supply. It has a soft power on and off button right here, which is also controllable from the computer, so you can have it turn itself off. Like, you can do a shutdown command. It's got a reset and a non-maskable interrupt button as well. And it has pin headers here to connect your LEDs and front panel switches on your board to it. So It's kind of cool that way. Anyways, I plugged in an ETX power supply and I started working on this. Well, I mean, I did a lot of troubleshooting, and fundamentally, there weren't any major issues with this board. The one problem that all these bodge wires are right here is that the ROM and RAM banking wasn't working yet, and Kevin actually knew that. He knew that there was a little bit of a problem with the way he designed the select logic for that would prevent these from working. So these bodge wires came later after I helped him kind of get his prototype working, so that would enable functional ROM and RAM banking. But you don't need that just to test the basic peripherals, because that just runs out of the regular RAM and out of the regular ROM, like none of the bank stuff. So that's what I was focusing on. In fact, I had taken out all of the extra RAM chips because those weren't needed. I had actually removed a bunch of the chips just to kind of make sure that I was eliminating any problems. But to try to figure out why, when Kevin tried to address the various peripherals like the sound chip and the VERA, nothing seemed to be working. That's what I started to really dig into. And I used my oscilloscope and I started looking at scope traces, and I started looking at data sheets for things. Now, there's no data sheet for the VERA, right? This was designed by someone. The FPGA code is all written by him. So the way this works, we have to look at that later. But the VIAs, the 6522s, the sound chip, the two sound chips, because I tested both, and the clock and that kind of stuff, those all have data sheets you can look at. So to boil it down to what was going on here and to what I figured out was that it was all issues with the way the chip select logic was selecting the peripherals. Now on a 6522 processor, there are timing diagrams that you look in the data sheet about how everything works. And the only signal, besides the address and the data bus that comes out of 6502, so when you're addressing peripherals, is the write pin, write enable. It's basically telling the chip, hey, the processor is writing to you right now, so please listen to the data bus and take that data in. Or it might look at the address bus too. But so like if you're writing to RAM, when the processor wants to write to it, there's also a write signal, and when it goes low, then it's telling that RAM chip, listen, I am writing to you now. Well, different chips need those signals to happen at different times. And also, there are different times when the chips look at the data bus to see like what the information is it needs to write to its memory or its register or whatever. Well, it turns out, like for instance, that the VIAs here, they need the chip enable line, which is generated by this select logic here. So that's like, you're writing to the very specific address space of the I/O port of these chips. That does the chip enable line. And then the write enable line comes from the CPU. Well, it turns out that these two chips, they need those lines directly. Like, they don't need them manipulated in any way. They just want them, boom, I want them direct, like right from the CPU or right from the select logic, no buffering, no nothing. But other chips, they want the little select lines to be ANDed to the clock signal. And that's a common 6502 thing where the 6502 has the clock signal going up and down and the processor's kind of working along those clock things. Well, with some chips, you need to take the clock signal, which goes low to high, and you need to AND it to these chip select lines so that basically the chip, and the VERA is an example of this, the VERA needs its write and its read, the chip select and the write enable signals to go low together at the same time and when the clock is high. So you basically AND those signals, well, with an inverter to the clock signal. It's all just, anyways, the long story short is it all comes down to timing. And the way Kevin had designed this second version was he took the write enable line, comes from the CPU, and he ANDed it with the clock. And he also did that with the I/O select lines. Well, when you do that, some of the components work, like the RAM and the ROM work fine, but the VIAs don't work at all. They just won't, like, you talk to them and they're not there. So when you try to use these, that doesn't work. So when I had my little LCD plugged in the user port here, my little 16x2, I wrote some code to talk to it, display hello, Adrian Black, whatever on it. It wasn't working. And that's because these chips weren't doing anything. So I wrote some code that just manipulated these chips to like toggle the outputs. Nothing. They weren't working at all. So I did a bodge on here that took away that ANDing of those signals, the write, enable, and chip select from the clock, and suddenly these started working. So I basically kind of started going down that path with all the different peripherals in here and testing which way they like it. You can read the data sheet and it's actually pretty clear about it. So the data sheet for these, it's clear what it wants. So it needs the clock signal, it needs those signals to not be ANDed. But then like the VERA, when we talked to the designer of this, it does need to be ANDed with the clock signal, and they also need to go low at the same time. And then I think like the SAA 1099 sound chip, here's this one, it needs the chip select line to not be ANDed, and then it needs the write enable to be ANDed. So that basically the write enable goes low after the chip select, and then that chip works reliably. It kind of works both ways, but it works more reliably when you AND just the write enable. So anyway, it was just a whole lot of that kind of stuff. It was just figuring out all the different permutations and then writing some test code in assembly language to test these various peripherals, and then looking at my oscilloscope to see, was that actually working? We had no working monitor. I had like no way to display text or keyboard or anything. I had to basically write assembly code on my PC with a cross assembler, put it in the ROM chip, power this thing up, and use my oscilloscope to try to figure out if it was actually generating anything. So yeah, in the process of doing the troubleshooting, I created several different test programs. Eventually, one of them was to test the video output here with the VERA. So I finally got that working, the Hello World thing. There was testing the 2 sound chips. I used Kevin's code for the YMF, and then I used some new code that I wrote. He sent me some test code for that too, but I just rewrote it for that, so that generated some sounds. I wrote test code for the VIAs. I wrote an LCD test script. That all worked. I could tell that the ROM and the RAM was working, not the banking, but everything else. I didn't test the stuff like the keyboard port, but that doesn't matter because it's through the VIAs. So as long as the VIA is working, you can do whatever you need to do to make the keyboard and the controllers work. So yeah, it was just a matter of kind of figuring that stuff out. Now, the one thing that had really thrown Kevin for a loop is the sound output circuitry that generates the analog sound that comes out of the headphone jack. There's a headphone jack right there. You plug it into there and I would play something and I wouldn't get anything back. Like you just had no sound. It turned out he had made a small error in the op amps of the output chain that goes to the headphone jack. So there was no sound, but I was running my test code and I would clip onto the chips and I would see sound. So I knew it was working. So then I looked at the schematics and I was like, well, I don't know analog circuitry that well, but pulling that chip out allows the sound to work. It's quieter than it should be, but it works. He's already fixed that. In fact, he told me what fix I need to do. There's like a bodge or something. I can put the chip back in and then the sound will work properly, like loudly again. So the first thing I did is I had the YMF generating some music and I called him on the phone. I was like, hey, Kevin, listen. And I played it and he heard the test sound. He's like, oh, I can't even believe that. So that was sort of the beginning, right, of kind of getting down the road and I just figuring out the stuff. And the worst thing is that Kevin's board, he had been trying a lot of different things for a long time, trying to get it working. And the reality was he was like so close, so many times to having it working. But I think like there was just several different variables. Like there was the sound, this sound output that wasn't working. So he might've had it playing sound, but he had this chip in there, so there was no sound. And he didn't check the pins on the, he didn't check like the digital analog converter here. And like he said, he had it other times, but you're trying over and over again to get something working, and just sometimes you don't try every possible combination. And then there was something else he said. I think this bodge right here, like for the LS245, I think he had put some sockets in there on his. Mine is permanently soldered, but on his first prototype, well, his first built one, he had just used some sockets, and apparently there was a bad socket, and it was just making bad contact. And he figured that out after I kind of got mine working. I said, okay, replicate the mods I've done, and he did. Still wasn't working. And then he figured out that the socket that he had stuck in here was bad and he wasn't getting all the signals through to the sound chips. So all his sound chip testing was thwarted by a dodgy socket right here. And once he took it off and just put these, I think he soldered his on, I don't know what he did exactly, it made it work. So I really feel like the most valuable thing I probably provided was a little bit of test code and a second set of eyes. And really, it's like anything. When you're working in a project and your head is down and you're working for so long, sometimes you miss things that you might not have otherwise missed because you've gone over everything like a million times. You're like, I don't understand, and it can be frustrating. And the second set of eyes to just go, hey, let me start from scratch, with information. I didn't rely on info from Kevin. I just sort of started on down my own path. That way, if there were anything that he might have recommended that maybe had caused a problem, I wouldn't have seen it. So I took my troubleshooting abilities and I just applied it to this board, and that resulted in a functioning board. Now, Kevin came up with this banking fix, which is what these wires are here, and that fixed the ROM and RAM banking. He was nearly there with the logic, just had a few small corrections. So Kevin got the guy who was designing the kernel to create a new kernel that supports this new ROM RAM banking that this board does, that's different than the emulator. And with that, we got it up and running. And if you watch his video, you'll see it's running, and he's able to run software that was developed for the emulator, and it works. Not everything works because, like I said, the emulator was designed to mimic the design of the previous revision of this, so the ROM RAM banking is different. So anything that uses the banking is going to fail until it's fixed. Now, it's minor changes that need to be done to that code to make it work on this. And I think the VERA might have had ever so slight changes as well done to it. But nonetheless, once the emulator is updated to match this, then anyone who goes and runs code and designs code for the emulator, it will work on the actual hardware. And since I've never been part of any project like this where like something is designed bespoke like this, that's really exciting. I really had a lot of like, look, it actually works moments with this. Because yeah, I didn't know where I was going with this. I didn't know if I was gonna be able to make this thing work. And to actually see things come up and initialize the screen and run code and generate sounds, it was so cool. So on this board now, yes, the kernel is working. I have that flashed in here. This thing boots up to the kernel. There are still some minor stability issues with this board, due to probably a little bit of like reflection issues. When you're running 8 megahertz, things start to get a little more difficult from a circuit design standpoint. When you look at those old computers like the Apple II and the VIC-20 and even the Commodore 128, 1, 2 megahertz, that's very different than 8 megahertz. And so there's some stuff a few things that need to be worked out. But absolutely, this board right now with these ridiculous leads on here totally works. Not everything is working simultaneously. Kevin did a couple extra bodges on his, like there's an extra chip flying over here to make the vias work. And that's because, back to what I mentioned about the way the chip select lines work, there are differences. Like those chips want something different than the VERA and the sound chips. And if you look at schematics of like the BBC Micro, which is a very complicated 6502 machine, all things considered, you'll notice that it takes all that into account. All those various things the chips want. Some want it ANDed with the clock, some don't, some want this delay, whatever. Like it has those exact design considerations. Like after we got this working, I started studying the schematics for the BBC Micro, and I'm like, oh, I can see exactly what they did here. I can see the way they're driving the 6522s on that versus other chips. It's funny how it's the same. That's what's gonna have to get done on here. So the next version will have a couple extra chips, or actually a few less probably, because they're taking off Kevin's taking off that sound chip, and I think the clock circuit's being simplified. So there will be some slight changes. But that means that the chips will get the chip select signals that they want, and the right enable signals that they want, and everything should work, which is really, really exciting. So I was really happy to be part of this project to help get this thing functioning and moving forward, and everyone's really excited. And I think the fact that the hardware is working means that there should be some movement on this project. I don't know when David is going to make another video on his channel about this, but I'm assuming that there will be some upcoming. Maybe it'll be when the new revision comes out. I'm not too sure like the time frame for that. And I'll obviously be available to help the entire team for Commander X16 anytime that they need some assistance. I'm more than willing to throw my troubleshooting, I wouldn't call it expertise, abilities, I guess, into this, because I think sometimes it's just that second set of eyes. That's all you need. I mean, like I said, Kevin was so close to having his working. It was just the smallest little things, and he was aware of everything I explained to him. Like nothing that I did was anything that he couldn't have done himself. But I think it's just that second set of eyes, that different perspective that I have versus say someone else. Like we all have different perspectives about doing things, right? And that really comes in valuable. I mean, it's not just in this type of thing, it's in anything. Very interesting stuff. And because this is such a new thing, there's no test code. I had to write the test code myself. There was no test code that was developed. So hopefully that one thing that will come out of my helping these guys is they will come up with some test code to help diagnose these in the future. Because clearly, when these are being manufactured, if you're building a kit and it's not working quite right, some code to run that to test would really help. Like even a light, like a diagnostic light to say, hey, I'm working. That doesn't exist on here right now. So there's no way to even like an Arduino, you can flash an LED. There's no way to flash an LED on here that's like built in the board. So there's no way to put a ROM in here just to see if it's executing code or not. You need to use a logic analyzer or a logic probe, I suppose, or an oscilloscope, ideally, to do any kind of testing. And that's not ideal for a homebrew computer. I mean, I threw in my few cents into the hat of like things I think this thing could need, and a few diagnostic aids, like a light on the VERA to say, hey, I'm working, would be incredibly useful. And the same on the board. But right now, those don't exist. So anyhow, I have talked a lot. This was supposed to be a short video. I hope this was a little bit insightful. I apologize for not having a video on this, specifically on the troubleshooting process. Like I said, I never thought I was actually going to get anywhere fixing this. I just thought I might have some insight, but I didn't really ever think that anything I did would ever matter, so to speak, with this board. That's why I didn't really do anything with this. It was only people's comments on Kevin's video, and I've even had a few on mine saying, hey, could you please talk about this? So that's what this video is. All right, well, here's a new camera angle I never used before. I have the camera still mounted on the mount over my bench, but I've tilted it up. So I'm sitting in my chair. This is normally where I'm working on stuff. That's the mail call stuff behind me there. So yeah, anyhow, so that's it for my Commander X16 video at the moment. Feel free to put comments and questions down in the comment section if you want to know a little bit more about what I tried to explain here and probably didn't do a very good job about. But yeah, that's it. So if you enjoyed this video, sure, give me a thumbs up. But if you didn't, you know what to do. Don't forget to check out the website for this thing, this project. Join the Facebook group if you want to talk to those guys about the designers and the people who come up with all this stuff. Check out the emulator so you can write some of your own software for this thing, because you know, this will come out in one form or another in real hardware eventually, so that your code can actually be written, I'm sorry, can be run on things. How cool is that? And subscribe to my channel if you haven't already. Check out 8-Bit Guy's channel and Kevin's channel. I think I've talked about this already a bunch, so I'm just repeating myself, so I apologize. Anyhow, that's gonna be it. Back to mail call videos next week. And I hope everyone is safe, happy, healthy, all those things. And I'll see you next time. Bye-bye.